Hi, guys, and welcome to our next section. In this section, we're going to spend several weeks talking about information extraction and knowledge graphs. So more commonly, you might think of this as named entity recognition, but we'll cover more concepts than that. So today, we're going to start by explaining information extraction, common tasks with information extraction, and then the next couple of lectures, we'll get into how to perform those tasks. So what is information extraction? Well, we deal with text all day. So, you might think about text literally on your phone calls, email, if I could stop with the email, right? Street signs, menus at a restaurant, and more. Television, the internet. Text is a major part of our life, just like language. So information can be defined in a lot of different ways, right? And that might be, I want to get the names from the text, the phone numbers from the text, people, events, relationships, etc. And so I have, my Google Calendar set up so that it pulls information that I've saved, like a concert I'm going to, or a hotel reservation. So how does it understand how to extract that information to save it? And why has it stopped working? So information extraction is gathering relevant information from text sources. And so, we might think about how Google does this. So if I Google Lady Gaga, just for fun, what happens is this summary on the side appears. Now, 90% of that looks like it's straight from Wikipedia, so I don't know exactly how much extraction there is, except that it grabbed the first paragraph. But the born and the parents and the other connections component is extracted from somewhere, right? And so they have people also ask these questions, and then they extract the answer to that question for you. So it's clearly a task that people do. Okay. And so a lot of data sources are structured. Okay, so if you're familiar with SQL, those databases are very structured. JSON, structured format. Table, structured format. Language, not so structured. And so if you were following along with our sort of processing raw text section, you can easily see that language is not structured. Okay, and the stuff that we're usually interested in is not as structured. If it's all in a SQL database, you have the luckiest job. Okay. So information extraction is also an unstructured task, and it can be fairly difficult. Thankfully, we have a lot of toolkits that help us with this. Okay. And fixed patterns are easier to recognize. So email is a fixed pattern. Okay. However, regular expressions can also be difficult. I was teaching class recently trying to like give some basic regular expressions. It probably took us like 30 minutes just to figure out how to exclude parentheses because I forgot you have to escape them. So there's always that issue of when you're using regular expressions, getting them right, okay? Because they come in different forms and flavors. Finding in names and relationships between items is a lot harder, okay? Because you have to first understand the idea of extracting a proper noun, like a name, but then also extract the relationship to that name in another place in the text. Okay. So I'm to my right here, I'm looking at is my two dogs are like turning in circles to lay down, right? So excuse me for being slightly distracted while they're being silly. They might make an appearance in this video. Because there's only so much you can do with your kids and your animals when you're working, right? All right, so a history of information extraction, very brief, like one slide. And the kind of claim the modern day start is in 1987-ish with the US Navy, okay? Which makes a lot of sense. The government would be very interested in this task because there are lots of documents, and how can we sort of summarize and acquire the information from them quickly? Okay. In the 2000s and 2010s, there were conferences that were organized by the National Institute of Standards and Technology to try to come up with ways to extract information and to process that information. And so these included these competitions for figuring out querying. And so things always go faster when there's competitions. So Netflix is very famous for saying, if you can write a machine learning algorithm that would better predict what score people are going to give on a movie we've recommended them, we'll buy it from you. And that was very successful for several years. They've changed it a lot now, but competitions can really help push a lot of these technologies forward. And so now information extraction is a very popular field, especially named entity recognition. However, it's also one of the most brittle or complicated fields because the models don't often generalize from one data source to another. So some examples. Let's say we want to tag news and other content for those trending headlines. So Google News's homepage has this sort of trending now concept of what people are looking at because they have that data, right? But then there's also summaries or reviews on Amazon where you can click on a concept to see the reviews that cover that concept. Okay, that would be Keyphrase Extraction. And a bunch of other places that we see these sort of trending comments, right? Like on Twitter, for example. Chatbots also have to understand people's questions. So if I said, what's the best coffee shop near me? Because science doesn't happen without coffee. Okay. It first has to extract that coffee is the what. I'm looking for coffee. And near me is a location to really answer that question accurately for me. Okay. And social media, with good information extraction, could be used to provide traffic updates. Right. And so if a bunch of people are posting about there's a giant collision on the highway or disaster updates. And so we've seen this even recently with the earthquake in Turkey. So that'll date this video, that there are ways that social media can be used to understand what's happening in real time. But it has to extract that information, or someone does. So, what can we do to do that? Then businesses might really be interested in information extraction from forms or receipts. So if we scan them in and use OCR, can we convert these documents into structured information? And you see that is getting better and better. So now if I take a picture of a receipt with my phone, I can actually highlight the text on it, because it figures out what pieces of information are important. But then how can we write a program that would take all of your business receipts and organize them into accounting? And that'd be great. Okay. The other cool thing that's really popular is cashing your check via picture. And so I remember when this was first implemented at these different banks, it's really cool because it is so convenient. Okay. That's an example of an NLP task. You don't think it would be, but it is, because it has to extract, right, all of the relevant information, the account number, the account holder, who it's going to, what the amount is, and more. Now, for example, what can we learn from from a piece of text, right? So here's the example from the textbook. It says, shortly after Apple used a new tax law last year to bring back a lot of its money, it's going to buy back its stock. Okay. So this has a couple of things in it, like Apple is a business. It has Apple's finance chief's name, right? And what is happening. Buybacks should be welcome news to shareholders, as that means the stock price is likely to climb. And so if I'm looking at the article, what I might learn is that it's about Apple, the company, not Apple, the fruit, right? So name disambiguation. It tells me who the CFO or the chief financial person is. It tells me what's going on, okay, stock buybacks. So how do we extract that information? Well, we could use keyword or key phrase extraction, which is what we'll cover code-wise today. And that's where we're extracting keywords from a document. This is so handy, especially as a scientist, because I could use it to help me search for articles that are relevant to something I'm working on, right? It's really useful for matching you to other things that you might want to read. If you're looking at something like Pocket, or which is a news aggregator, or similar types of products, okay, based on their key phrases that they have in their ads. So you can always tell when someone's trying to game the metadata system is when their product description has so many crazy different words in it that don't make sense because they're trying to game the system of keyword extraction. Okay. Named entity recognition, or NER, is arguably one of the most recognizable tasks in NLP. Okay. And that's where you're extracting company names, proper names, places, any kind of proper noun in a document. But also, surprisingly, things like money, dates, wars, roads, laws, and more. Okay. So people think about it as names because it's in the title, named entity recognition. But it actually is quite a bit of other information as well. Okay. But then you have the problem of, how do I know that Albert Einstein is the Einstein singular name, which might also be a scientist? Like, how do I understand that two names mean the same person or entity and two things mean different entities? Okay, because Einstein's is also a really great bagel place. So name entity disambiguation helps us look at two similar items and decide if they're the same concept or not. Okay. And then relation extraction. And this is figuring out the relationships in text. So if I said Scott kicked the ball, you could say that you would understand that Scott is the one who's doing the kicking. Okay. And that can often be done with dependency parsing, but there are a couple of other co-reference options as well. Now, the more complicated tasks, so these two slides are split for a reason, are taking those first 4 or 5 options and applying them to then do something else. So event extraction is a named entity task because you're extracting events and there are date and time information. Okay? But then you're also using relationship information to relate them to other texts. So let's say that you are searching for information about the earthquake in Turkey. So you are hoping that you get articles all about that and not about something else that happens to also be going on in Turkey, or about a different earthquake in California. And so event extraction allows us to map that those two things are the same or different. Okay. Temporal information extraction is things like getting dates and times. So how Google is able to take my emails and add calendar events to my calendar. I didn't realize I had become so reliant on this until it didn't. It stopped working for certain emails, like hotels emails, that I was like, I don't know what's going on. When is my plane flight? When is this hotel reservation? Okay, so now I have to make sure I enter them. But a lot of programs do this, and it's really convenient and useful to have a program that can extract that information and save it for you, for example. And then template filling would be extracting the information and then plugging it into a template. So like it gives me a weather update. And so you extract the information like weather and tell people it's 90 degrees outside. Or 40 something for my Celsius friends. Okay. Now a caveat. We often think, it's a typo, we often think of supervised learning as the answer to everything. Okay. And this is admittedly a very popular form of math that does tend to work pretty well. However, most information extraction is a mix of supervised and rule-based learning systems because supervised learning doesn't quite capture it sometimes. Okay. Because most IE systems are fairly brittle. Okay, they are tailored to a specific area of interest or a specific task. There is no system that will pull every name ever from a document. Okay, and if you have a set of objects or names, you can create your own, okay, which we'll look at how to do. And more often than not, people pay for these systems. Okay, so using Microsoft's, Google's, and there's a couple of others with APIs that you can use to run your text through and get the entities out of them. Now, those systems are less brittle because they're large. Okay, individually tailored systems are more brittle because they only will work for the types of things they've been trained on. Okay, they do not generalize well. So a pipeline for information extraction might include raw text. Okay, cool. Then we'll break that text into its components, its sentences, and its words. Okay. Shouldn't be too terribly hard. Now, key phrase extraction can happen at the word tokenization level. I'd actually argue that key phrase extraction tends to happen at the sentence level because it's extracting entire phrases and not just words. Okay. Then we can do part of speech tagging, which we'll cover a little bit here in a couple slides. And from there, we could use that to do named entity recognition because most named entities are proper nouns. So if you can label your parts of speech with things like noun, you're halfway there. Okay. Then we can do syntactic parsing. This would be breaking down the sentence into its syntax components, noun phrase, verb phrase, preposition phrase. And that's where entity disambiguation can occur. Co-reference resolution allows us to figure out how things are related to each other in the text, whereas where entity disambiguation also occurs. And then relation extraction and event extraction tend to happen at the co-reference level. So these are all the different components of an IE system, and you can tell that they probably are different levels of difficulty based on how many steps you have to run them through. So it's more of a fine-grained approach, right? I think you could program a deep learning model and just throw everything at it. I just don't know how well I think it would work or how much training you would need. And the training data for this can be hard to acquire. So what we can do to create these pipelines is really think about part of speech tagging. So I took some of my old notes to pull together so that we could make sure that you understood part of speech tagging, because I think this textbook and the other textbook kind of takes it as an assumption that you've already heard of this and you know how to do it. So we'll cover a little bit more of that. But what it is in general is giving each individual token, like each individual word, a part of speech, noun, verb, preposition. Okay? And because part of speech taggers really are a well-known solution. There is no need to program your own unless you're going to do something with in a language that's not well defined or a very specific type of subgroup. For example, like if you were going to process Twitch chats, okay, those are a very specific subgroup with a lot of words that wouldn't occur in a normal part of speech tagger. Okay. But most NLP taggers can do this with a very high accuracy. Okay? And you can build your own with over a 90% accuracy in like 3 or 4 lines of code. So I really like spacies. It's quite good. The best one is actually a program in R, and it's called UDPipe, which stands for Universal Dependencies Pipe. And that's the one that I tend to use when I'm mixing and matching my code back and forth. Okay, but spacy will get you there pretty good. And then we can also do co-reference solutions, right? Relating the fact that multiple references are the same entity or separating them, disambiguating them, so that we can kind of cluster together objects that are the same. Now, let's get a little bit into part of speech tagging because this is sort of critical component to most of information extraction. So let's back up and talk about syntax. So syntax comes into play in a bunch of places. Part of speech tagging is heavily reliant on syntax. Okay, and syntactic parsing is all about syntax. So what the heck is syntax? Okay, and not like the computer kind, like the language kind. So it's a set of rules that we use to put together well-formed sentences. Okay. Now, don't tell my linguistics professor that I'm going to tell you that syntax and grammar are effectively the same idea when it comes to computers. But the idea is that syntax allows us to put together sentences that we know are grammatically correct. Okay? And the grammar helps us translate it into meaning. Right? So word order is very important for our understanding of meaning in most languages, where the actor, the person doing the action, is the first thing in the sentence, and the thing being acted upon, Scott kicked the ball, is the thing towards the end of the sentence. Okay? So word order, really important. Tensing on verbs, also really important marker. Okay? So syntax has a lot of components to it. It's not just word order. It also has subject-verb agreement, and tenses, and some other rules to help us understand what's going on. Okay. So we start with the words. We use words to build up into phrases. We take those phrases and build them into clauses, clauses into sentences, which is mostly where NER rests. And then that could also be built into paragraphs. And the largest amount of text is called discourse. This is a lot of text. Okay. And so a constituent is a member of the current set that I'm examining. So words are constituents of phrases and sentences, whereas sentences and phrases are members of sentences, and sentences are constituents in paragraphs. Okay. So if you ever hear the phrase constituency parsing, I like this book calls it syntactic parsing. That to me is a little bit clearer, but constituency parsing is just figuring out what words are happening, syntax parsing, what is happening in this sentence. Okay. Now, I just said that word order is one of the most important rules. Okay, it's honestly the most important rule for transforming individual concepts on the page into meaning. Okay. So if we scramble the words in a sentence, that meaning is going to be lost because we use word order and the structure of the sentence to understand what's happening. Okay. But it's not our only rule. So this is a very famous Chomsky sentence where he said, colorless green ideas sleep furiously. Syntactically, that is perfectly correct. Okay. It is in the proper word order to be a well-formed sentence. However, it makes no sense, right? Unless you've heard it 1,000 times like I have, but it doesn't make any sense. But word order does give us the most clues on how to parse a sentence. So a very famous NLP task is called parsing. Okay, parsing is the kind of global term for how we break sentences down. So the book is calling this syntactic parsing, but you might also hear constituency parsing and or dependency parsing. These are just different ways of conceptualizing the structure in a sentence and how that tells us something about what it means. So what are words? And this feels like I just know what they are, but they do have a definition. So they're the smallest unit of independent language with meaning. Okay. So the letter S is not a word. It does have meaning, but it's not an independent meaning. Okay. So morphemes are the smallest unit of meaning. Okay. However, they're not always independent. So like if I say you can retake the exam, that means to do over, right? Is a morpheme. It does have a smallest unit of meaning, but it's not independent. I couldn't just say re in a text, right? We're talking about the regular expressions package, but it does not stand on its own, is what I'm trying to say. Okay, so cat is a word and one morpheme. Cats is also a single word, but two morphemes, because that S tells us something useful, plural, more than one, but it is not a word that can stand, an independent thing that can stand on its own. Okay, it has to be paired with the cats. So we'll spend this section thinking about how to classify words into their part of speech very briefly so that we can then go back to Keyphrase extraction and NER. Okay. So what are some parts of speech? Well, we could call things nouns. Nouns are probably the most important component for information extraction, but the verbs are useful too. Excuse me, it's like the mid-afternoon yawns, right? So nouns are words that depict objects or entities, but they can also be very abstract, like truth is a noun. Okay. Verbs are the actors in the sentence, right? So they depict some sort of action, some sort of state. I'm sleepy, an occurrence of something that happens. Okay. Adjectives are words that modify nouns. So green is usually an adjective. Adverbs, however, are words that modify or qualify verbs. There's also auxiliary verbs. So, there's a couple of different types. So there's proper nouns and regular nouns, okay? And then there's verbs and past tense verbs and auxiliary verbs. Okay? There's also something called a modal, that's could, should, would. So there are a bunch of types sometimes within these types. So we're doing the kind kind of the big categories. But then we also have things like prepositions, in, of, determinants, the, a, an, conjunctions, but, and. So there are somewhere between 10 and 15 very common parts of speech, and then they can get more fine-grained from there. So let's do a quick example. So I've used this example before because it's just a really great one because it's a stupidly complex sentence. And so we're going to import spacy and pandas, and then we're going to load the English language module. And so the sentence comes from a big controversy that was going on with some academic, I don't even remember who said something unfortunate on Twitter. Okay? And the university issued this statement, not our university. This is not from Harrisburg. This is just one of those things I saw on Twitter. Okay. The university that person worked at said we cannot, nor would we fire Professor Person. Okay. Fire is an interesting word here because it's most commonly a noun. In this scenario, it's a verb. And so you're going to see that's going to cause us problems. For his post as a private citizen, as vile and stupid as they are, because the First Amendment of the United States Constitution forbids us to do so, the provost, not our provost, a different one, wrote in a letter, right? So this was from a summary article about the incident. Now, what I can do is tag that sentence. So the NLP function that we load will allow us to create part of speech tags and dependency parsing and NER. So spacy kind of does a lot of these things. And we'll tell it to print. Okay, so we're going to print a tuple, a 3-part tuple. So I think there's this bad tendency of folks to think that tuples mean two. It just kind of sounds like it the way they're pronounced. If you want to call it a tuple instead, I've also heard that. But we're going to go 3-part section. We're going to print the actual word that it parsed, the word dot tag. This is the more fine-grained tag for the word usually. And then the word dot part of speech. These are usually a bit more interpretable. Okay. And I think they're the universal part of speech system. So print all 3 of those for each word in our sentence. Okay. Now it's only going to show me, if you scroll, you can see all of it. And what we see, first thing, by creating a list of tuples, we can easily convert this to pandas, which is what I did. Right? And what we see is we is a pronoun. Okay. Can is an interesting one. It's an auxiliary verb or a modal. It's the MD. Not here as a participle. Okay, punctuation, nor our conjunction. Would we, a modal verb and a pronoun. Fire. Now, fire, it did get correct. Okay, so it figured out that that is a verb, even though it's most commonly a noun. So words that change parts of speech can be really difficult. And you would think that wouldn't happen very often, but actually it's really common for words to have multiple parts of speech. Okay. Professor Person got marked as a proper noun because they were capitalized. Okay. For his posts, and so it keeps going. So now that we have these parts of speech, we could, in theory, just pull out all the nouns and see what we get. Okay. Now, it's a little better to actually use information extraction than that, but it is not a bad place to start. Okay. Now, phrases are one or more words that kind of can do one of the following things. Okay, it can be a noun phrase where the noun is the head word. Think of head word as like the word in charge. It usually means the first word, but a noun phrase. Let's see. The dogs are taking a nap. Okay, that would be the dogs. So it depicts the actor in the sentence. Unless you've got a passive voice sentence, which is a whole nother set of concerns. Okay. The verb phrase is where the verb acts as the main word in charge and it depicts the action. So the dogs are asleep. This would be are asleep. Within those 2 phrases, then we can then also define any prepositional phrases that happen. So where the preposition modifies the phrase, if I say going up the stairs would be the prepositional phrase that is attached to the verb. So hopefully you're going to see now how we're going to do some of this relationship extraction. Okay. We can also have adverb or adjective phrases that modify either a verb or a noun phrase. So the dogs are asleep. Asleep here is actually an adjective phrase because it's modifying dog. Okay. And so we'll cover those more when we do a little bit of entity recognition and dependency parsing in this section. And but first, let's look at how we can tag parts of speech to be able to do that phrase tagging, which is what IE rests on. Okay. And so understanding words and phrases also helps us understand the grammar, which is our set of rules, right, on how to construct sentences to be translated into meaning. So talking about grammar, right? So I kind of want to mention the two big ones, okay? Because this comes up if we go back and we look, right? So let's first, 2 seconds, let's go back here. You know, we have to find some system that figures out how to tag parts of speech because it's going to be so critical for the grammar part. And if we go back and look at any i.e. pipelines here, what's happening is part of speech tagging is embedded in the pipeline, and parsing here that's the grammar part. The syntactic parsing involves some form of grammar. And so we have to, you know, we can do keyphrase extraction actually without part of speech tagging, but it does go better if you do it with part of speech tagging. We can do NER without any parsing. But once you start getting disambiguation and relationship extracting, you've got to figure out parsing as well. Okay, so let's go talk about some grammars so that we can get to parsing. Okay. So dependency grammar. So grammar defines the way that we parse. This is how these two things are connected. Okay. So dependency grammar is really good for information extraction because what it does is it tells you how the words in the sentence are dependent on each other, their relationship to each other. One is the noun modifier. The other one is the action in the sentence. Okay. This is often verb focused because the verb in a sentence makes up all the rules. It determines the subject verb matching. I walk, you walk, they walk, he walks. English is dumb. Okay. That third person singular is weird in English. Okay. We walk, they walk, she walks. Okay. So that verb determines what can happen, right? It also tells you tense. Some verbs are what's called transitive or intransitive or ditransitive or dative, sometimes is what's called. And these are ones that have to have direct objects or not. So the verb it's the boss of the sentence. Okay. And so when we're doing dependency parsing, we look at the part of speech and those word orders to determine dependencies. And that's embedded into spacy. Okay. Constituency grammar is kind of like the old school way of parsing sentences, but can still be very useful at understanding ambiguity of sentences, complexity of sentences, and can also be used to help build sentences like in a chatbot. Okay. Sometimes these are called phrase structure grammars, and they build them sort of hierarchically. Now, constituency grammar for a long time was more commonly used because the rules are very structured. Okay. Sentences break into noun phrases and verb phrases. Noun phrases usually contain determiners, adjectives, and nouns. Verb phrases tend to contain verbs and or prepositional phrases. So there's a lot of rules there that we can use to capture most of language. Now, dependency parsing is sometimes driven by constituency parsing. So making these cute little trees of a sentence, you can then convert it into a dependency tree. Okay. And so all of that's going to be really useful later for our disambiguation. Okay. Now, quick note on part of speech taggers, because I want to talk about tag sets. There are many parts of speech. A noun could be labeled as a noun, a plural noun, a proper noun, a pronoun, which is a different thing, etc. A verb could just be labeled verb, but it also could be modals or present tense, past tense, okay, present participle, future tense. Conjunctions can be coordinated conjunctions, subordinating conjunctions, or just conjunctions, and on and on and on. Okay. One of the more complex systems of tagging with CONLL or with the Brown corpus has like 55 different parts of speech. Okay. And you're like, I didn't think I could name more than 10. Well, what that does is it can make systems complicated and difficult to compare, actually. And when you have 55 different tags, that makes it actually quite hard to be accurate, although the part of speech taggers are really good, okay, even with this complexity. And so what I always tell folks is you have to define the level of specificity that you want to work with. If you're going to program your own, I highly recommend programming it to be more complex, to have more tags, because you can always go simpler. But if you wanted to go from simple to complex, you have to start over. Okay. And so there are different corpora that you can use to train your model. Okay, corpus is just a large body of training text. It's actually just a large body of text. In this scenario, it's a large body of text that's appropriately structured for training. So the Brown corpus is one of the most popular teaching tools because it doesn't make it very easy to build models. I have done it for a long time. But there are other popular training data sets as well. Okay. Now the Brown corpus has a complex system, which we could then convert to a simpler system. And so it just kind of depends on the training that's used on that tagger. Okay, and different taggers have different training rules. And those sets of tags that people use are called tag sets. So there's one called the universal tag set that most systems have. Okay, this is the less complex one. The problem with the universal tag set is it's actually not universal. What'll happen is that you will see that different, so if you pick a couple of parsers in R and a couple of parsers in Python, you'll find that the universal tag set is somewhat inconsistent. So they just tend to be, the labels tend to be slightly different, and some of them tend to have a couple more than others. So in theory, the universal tag set has 10. In practice, it's like 10 to 15, depending on which tagger you're using. Okay, by tagger, I mean whichever program you're picking. Okay, so Spacy has a tagger, NLTK has a tagger, and there are a couple of packages in R. So what do we use to tag? I've told you that you have to do part of speech tagging to get to parsing, and parsing is going to be necessary for some of these IE tasks. Like what? Okay, fine. I believe you that I have to understand this part of speech tagging thing, but what is it doing? Right? What are the things that we can use to figure out parts of speech? Well, you could just look it up. It literally could open a computer dictionary and say this word is a noun. Okay? Like fire, for example. Most commonly, fire is a noun. In our example sentence, fire was a verb. Okay. So we can use something like WordNet, which is a large dictionary, or Penn Tree Bank, which is a tree bank. Tree banks is a very specific word, which is essentially a large dictionary. And that one's in English. We can just look it up. Okay, that's not actually a very good system because words can be multiple parts of speech. It's fast, but full of errors. And I said that part of speech taggers are actually really good. So what else could we do? Okay. And why are they full of errors? And one of them is polysemy. Okay. If you get nothing else out of this class, there are two things I want you to understand. The first one is that polysemy is what makes NLP one of the most difficult things. Polysemy is that individual words can have multiple meanings. Okay. And not even just like different shades of meaning. Like the word bank is a very popular example because it could mean riverbank, it could be money bank. Okay. And then different words that have the same spelling can have very different meanings, but it's disambiguated with pronunciation. So wind and wind are spelled the exact same way. So to a computer, it's not going to know the difference. To a human, when you hear it out loud, you go, okay. When you're reading it, you use context clues. Okay, so polysemy, very difficult And this is why word sense disambiguation, understanding which word they meant in context, is something that a lot of computer programs work on. What's the other thing I'd want you to get? The ambiguity in language and creativity in which we can combine sentences also makes NLP very hard. So the things that make us human, which is creativity and the ability to flexibly use words to mean different things, are the things that make it hard for computers to process. Now, what's something else I could do? Well, I could look at morphological cues. So this works better in languages that aren't English, because English, again, is 3 languages hiding in a trench coat pretending to be one. But some languages have very regularized forms of words. So like in English, past tense, ed. Okay? So I could say everything that ends in ed is a past tense verb. Okay? I would be right more often than not, but there are a lot of exceptions. Okay? I could look for anything with an S on the end to say it's a plural noun. Okay, actually, on that one, I'd probably be more wrong than often than not, but you get the idea. So ing might indicate that it's a verb in the what's called present participle tense or gerund tense. Okay. ly most likely is an adverb. That's pretty consistent in English. It's not perfect, but it's pretty consistent. Now that works pretty well, but it's still prone to errors. Like the word morning is an ing word that is not a verb. Okay. A couple more options. You can also use syntactic clues. Okay, this is the context or the words around it to help us determine parts of speech. This is like sequential processing, which you'll find out is very popular for information extraction tasks, where it uses the context of the things around it to help you determine what something is. Okay? This is what happens when you Google something. Or as you're typing, new systems now, and the first time this popped up in my email, I was like, what is happening? Where it's using the previously found words to help you predict what comes next. Okay, that's a sequential processing system. A lot of times they're Monte Carlo, Markov chain Monte Carlos, but that's still sequential. It understands the order of things. Okay. And that can be very slow, because to do that, you have to parse these bigger units of text and you have to have a lot more training data. But it is more accurate. Okay. And the last thing we could do is actually use word meaning. So word meaning can help you determine which class it is. So if I know that the word fire means to relieve someone of their job, okay, that's a verb, because the meaning tells me that it's not the noun form. Okay, and that's actually exceptionally difficult, because to understand which concept meaning it should be, you have to do word sense disambiguation, and to do word sense disambiguation, you already need to know the part of speech. So this is something that we do. Okay, this is context clues. Okay, by what's going on in the sentence around it, but it's much harder for computers to do because of multiple word meanings for the same sets of strings. All right, now that we've taken our slight detour, let's come back. And let's look at key phrase extraction. Okay, so we're going to talk about how to do key phrase extraction, and I'm going to give you some caveats and some simple things that you can start with. But if I look at what do people use key phrase extraction for? Like, why might I be interested in this? So this is from Amazon. Okay. And this is where you can flip through reviews and look at reviews that have whatever you're interested in looking for. So easy to install. Okay. Tell me if those reviews, like, let me see those reviews, because that will have easy and not easy to install. Okay. Wall mount works well. Okay, solid bedroom. And so I could search through objects towards what I'm interested in reading about. Okay, so Amazon uses this to help you find reviews that might help you decide if you want to buy something. And so key phrase extraction is useful for search and information retrieval, document tagging, and summarization. This is its shining moments. So I'm about to start using this for a project. I haven't done a whole lot of it. I've usually more used topic modeling to help me find themes. But now we're trying to find exact phrases in scientific articles. And I'm excited and frightened because there are going to be a lot of different ways to say the same thing. So thinking about how do we combine like forms? Okay. And so this is a supervised and an unsupervised learning task in machine learning. So people do it both ways. But the supervised tasks require text with the key phrases already embedded to train the model. Okay. And that may take a lot of time and effort for you to build so that you can build the model. And therefore, unsupervised approaches don't require this, and they're more popular. Right? Unsupervised approaches, way more popular. Okay. Also very easy to code when you can get your packages to play along together. Okay. And I'll talk about that in a minute. So what it does, here's how it works, is it builds this like graph. So when we get to the end of this chapter, we'll talk about how to build a knowledge graph, okay, which you could do with your extracted key phrases, but it'll build this graph. Okay. In network models, anytime you have like a bubble and little connections to each other, that's a network model. Okay. Each node tends to be a key phrase or an individual word. Okay. Or it can also be a person if we're doing person relationships. Okay. Or entity relation. Co-referencing sometimes is what it's called. So we've got all these little nodes. Then the nodes themselves are weighted for importance to the document. Okay. And so if I could think about like a word cloud where bigger words are more frequent, it's the same idea. Words with higher weights are more important to that document. And if you've ever done topic modeling, that's a little bit how that works. Okay. And the weights indicate our strength to the document. So higher is more, 0 is it's not. Okay. Then we connect those nodes to each other, usually by co-frequencies. Okay. And return the top in number of nodes. So take a really heavily weighted node and its friends, basically, things that are highly interconnected. Okay. And this is part of what's called network analysis, which is a kind of a complicated way of figuring out how things are related to each other. Okay. Some people have done this network analysis very similar to social networking analysis, which is connections between people. Okay. But we can also use it for words. Okay. And so how things are denoted as top? Like what is top? Right. And so it could be word frequency. So things that are more frequent are more likely than not the things that are going on in the text, minus things like determinants, the and a, prepositions of, those are very frequent words that don't add a whole lot to the text. So back to part of speech tagging. We could pull the big four. Okay, nouns, verbs, adjectives, and adverbs. I've always called these the big four because they explain the meaning in the text. The other words are function words, prepositions, conjunctions, determinants, all the rest of them, hold the sentence together. They're the glue in the text to help structure the sentence in a way to provide meaning. And so they're both important. So in this case, we're not going to drop stop words because the stop words help us understand and process the sentence. So parsing requires stop words. But nouns that are more frequent might be what the text is about. Okay. And then you grab its interconnectedness. So what you can have are these like little local clusters. So here's a set of keywords that all cluster together and they're all interconnected to each other. So that's likely pretty important. Okay. And what the difference is, so there's one called yake, rake, there's Bert, there's a couple of them. And those all differ in their approach to providing that extraction, the weights, and the connections. So while there are 4 to 6 popular algorithms, they're all doing the same idea. They'll give you different answers, though, because they're assigning the weights and the connections differently, and also extracting differently. So I tell you to run a couple and see which one you think provides you the most coherent results. Okay. All right. Now onto the technical part. To do this, we're going to use textacy, spacy, and a document that has the history of NLP in it. Okay. And so this will allow us to extract maybe names and other pieces of information, not names. We haven't gotten there yet. Sorry, that's next week. The key phrases. So what are the most important components to NLP? right? Probably language, you'd think. Right? And so I'm reading in a text file. So I'm practicing some of the skills that we learned in our last sets of lectures by reading in a text file. And I've printed out just a little bit of it down here on the screen for you. Now, as of making this lecture, Network X, which is the package that it uses to do a lot of this work, has updated to 3.0. Textacy in the development branch has dealt with this because I find that Python packages tend to just randomly remove functions, rename functions, and restructure the structure of their package willy-nilly. I'm sure there are reasons, and I'm sure there's a cultural history to Python package development that explains this, but I just find that every time I use either a new textbook or I go to look at a how-to guide, if it's more than a year old, there are days and times where it's like, okay, well, what has it changed to now? Okay, what has changed? Like, scikit-learn recently changed their confusion matrix. Confusion matrices have not changed. They don't change. They just are. Like, why would they change their function? Right. So this is my warning, and hopefully, in a month, this will be a dated conversation. But until then, if you are following along and you're having problems getting this to work, you need to install a lower version of Network X, less than 3.0. So that might be 2.8.8 with textacy, and then it'll run fine. Okay. The other issue, once textacy updates, which I think will be fairly soon, I went and asked on their GitHub, and they were very, very quick to respond. So thanks, team. You may need Python 3.9. So you may not want to upgrade textacy if you don't have Python 3.9 quite yet. And so just kind of a warning. If you have issues with these keyword extraction functions, you might consider downgrading Network X first, and then maybe downgrading textacy a little bit as well. But if you have Python 3.9, upgrade them both. Okay, soon. Okay. And so they have plans to make it work. And so if you're following along with me and using RStudio, all I had to do to fix this was install Network X less than 3.0. Okay. If you are using Jupyter, you might have to say pip install. You can use the same basic kind of code to do that. Conda is the same way. Okay. And that will just uninstall the newest version of Network X and install a lower version. Okay. And as far as I can tell, it doesn't really affect much else. Now, let's use textacy to load a spacy language. And we're going to use our Ian Core Web Small. And we're going to disable the parser because it's slow. So we're going to make a spacy doc. And this is very similar to doing NLP, load NLP in our spacy pipeline, and then process it with NLP, and then use textacy. But to show you a slightly different format of the pipeline, we could have textacy load the model and tell it to make it into a spacy formatted output. So I'm going to show you two of them. Text rank, very popular, and SG rank, okay, also very popular. And so we're going to say, okay, the keywords, key phrases for a combination of key phrases and weights, we could tell it to also print the weights, but we didn't. Okay. Are you ready for this? textacy.extract.keyterms.textrank. Okay. If you're looking at the textbook, it says .ke. That is old. Okay. So textacy.extract.keyterms.textrank. Okay. On our doc, we will normalize by using the lemma, right? So we're going to convert words back to their original root word with lemmatization. So this does not stem, it lemmatizes. I take the top 5. And so the history of NLP, successful natural language processing system, okay, natural language system, statistical natural language processing, natural language task. Pretty cool. Those are just all different forms of the way to say NLP. Okay? And statistical machine translation. And so with a history of NLP, machine translation features very heavily in this. So I think it did a pretty good job. Okay? And so I could use this to not read the article. Okay? Wouldn't know a whole lot else about it, except that the history of NLP involves NLP, machine learning, and making language systems. Okay? Now I can do that same thing with SG rank. Okay? And notice how the answers are very different. Okay? So we've got natural language processing system. I think that one's the same. Statistical machine translation, early research, late 1980s. Okay? So early research makes some sense because it's kind of telling you that this early research leads into the stuff that you see now. Not too surprising. Late 1980s actually also makes some sense because that's when things really took off, when the computer became something that many people could afford, as opposed to only universities and big businesses, and they became a lot smaller, okay, and more powerful. And now we have computers that, sitting on my desktop that I'm recording this with that are more powerful, like 8 billion times more powerful than what we used to send someone to the moon with. And I'm carrying around a computer in my pocket all the time. So, what the toolkits we have now are just amazing. Okay. And so I wanted to give some other examples in case you can't make textacy work. So the Summa package also does some cool keyword processing. And then there's 2 articles that I recommend that I used when my whole system broke down and I couldn't get anything to work, that also include BERT, which I think is pretty cool, Yake, which is yet another keyword extractor, Rake, which is a keyword extractor as well. So a couple different options. Okay. I like Summa because it's pretty easy. So from Summa, import keywords. Okay, keywords.keywords. Pretty simple. And I can have it print those keywords, and it also will print those weights for us. So on the same text, we got learning and learn. So the nice thing about spacy is that it limitized them. So learning and learn became the same concept. Okay. Data systems, that sounds kind of good. We've got results and result. Those are the same word. Real language, translation, and base. I did 10 of them here. Okay. So notice here that these are just keywords, though. Okay, this isn't key phrases. This one's keywords. So what do I have to do to get it ready, right? So one, how long should the phrases be, and like kind of what do I have to do? Okay. So some key things we need to think about. How long should the phrases be? Okay, because a lot of the first ones from the text rank algorithm gave me very, very similar phrases. And so it might be that I should just like use the phrase natural language and then have things like machine translation, systems, that kind of stuff. What parts of speech should we use or ignore? So getting the text ready for this is not a whole lot of work. Basically, just as long as it's not full of junk, right? HTML or other kinds of junk. But when it's doing the internal processing, should I ignore specific parts of speech, right? So should keywords include key phrases? Should they include function words or not? Okay, should they start with function words like be, in, the, not the is a determinant, but that kind of stuff. And what do we do about this overlapping phrase problem? Because obviously that happened in all of those algorithms. Okay. Well, the overlapping phrase problem we can actually deal with a little bit, but in general, key phrase extraction is sensitive to document lengths. Okay, and it's actually a weird thing that longer is more problematic. And so if you have a really long piece of text, the suggestion is to use the beginning and the end, because that's usually when people introduce and conclude. Okay. This reminds me of reading research papers where you read the introduction and the discussion and don't read all the boring parts in the middle. Okay. For me, I read all the boring parts in the middle and ignore the rest. Okay. Overlapping phrases, which we'll talk about this code down here at the bottom, and then unwanted words like prepositions. Okay. So one way to deal with the overlapping phrases is textacy. Okay. So I set my terms up. I picked out my terms from textacy.extract.keywords.textrank. Okay. Here are all my terms. And then I can use a utility function in textacy called aggregate term variance, which will try to combine like terms that have very high intercorrelations, basically, and have a lot of the same words. Okay. So successful natural language processing system combines a lot of the like system ones. And then we have statistical natural language processing and statistical machine translation system. Okay. So notice that the first couple are combinations of the ones we've already seen. Okay, and so that's where we're going to stop. We'll save named entity recognition for the next lecture, and then we'll also cover some of the other tasks and making knowledge graphs in the lecture after that. So come back for some more information extraction notes, and I will see you guys next week.